Okay, I think we can start. Not a lot of people today on Zoom. Okay, there is Jorge. Hi, Jorge. Okay, I think then we can start. That's fine. Sorry about being so late. But the previous guy here is that's so nice. Geez, okay. Where's Chuck? Sick. Okay, so any questions so far, maybe from previous lectures? I think last time we covered the preliminaries on regularity. And today we're going to start F-singularities, properly speaking. And to do that, we need to talk about the Kunz's theorem that we mentioned briefly last time. But the idea is to prove it today so that you see that it's true. So section 2 is all about Frobenius and the wonderful Kunz's theorem. Okay, let me just get my phone too, so that I know the time better. Okay, so what is the story here? So for this, we're going to take any Noetherian ring. So from now on, every ring is Noetherian unless otherwise stated. And the whole point is that we are going to assume that it's an FP algebra. This is to say, remember, P is a prime number and is the kernel of the canonical ring map from Z to R. Right? This is the characteristic of R. And so the wonderful thing is that then the following mapping, you take an element R in R and you raise it to the P power. This is a ring homomorphism. It's actually an FP algebra map. Homomorphism. Okay, so what does this mean? That there is an FP algebra map? That it has to commute with FP too, right? And why is that true? What is the Frobenius of FP? You know the answer? What happens if you have an element of FP and you raise to the P power? What happens? It's a theorem in basic number theory. It's the identity, right? Because, well, let's remember this for math. It's called Little's theorem or something like this, right? Little theorem says that x to the p is always, well, to the p minus 1 is congruent to x modulo p for all x in z. It's just p to 1, right? That's for Math's Little theorem. But you can say this means that x to the p is congruent to x modulo p. Right? In other words, the Frobenius of FP is the identity map. right? That's why Frobenius is a relative thing. It's a homomorphism of FP algebras as well. Okay, is that okay? It's a trivial observation, but it's an important one. Okay, let me. This is challenging. Okay, the other thing to say is that the power of Frobenius also comes from iterating the map. So you can take the iteration of F, right? So what you do is that you raise R to the P to the E, right? For any E non-negative integer, right? We're going to agree that F to the 0 is the identity, right? That's not hard to believe. And actually, just from now on, it's just impossible for me not to do this. For me, always Q is P to the E. It's just notation, okay? So we're going to follow that convention. So other things we're going to do is that the image of Frobenius, let's do it like this, or yeah. So the image of Frobenius, so you have Frobenius here, and so the image is going to be denoted by R to the Q. Okay. Remark that is going to be an exercise for you. It's very important from an algebra geometric point of view. Is that the spectrum of F to the E. So this is a map from spec R to spec R. Right? It's just a contraction of prime ideals along Frobenius. The point is that this is the identity. Okay? So in other words, Frobenius sees no topology in a sense. It's a purely ring theoretic phenomenon. So it's a scheme theoretic phenomenon, really. So more notation we're going to follow here. So this is another part of standard notation here. We're going to use it from time to time, I suppose. So it's based on the following. So, well, first of all, notice that R is reduced if and only if Frobenius is what? So if R is reduced, Frobenius is injective, and the converse is true, actually. So actually, this is the first hint that Frobenius detects singularity, because reducedness is a singularity property, right? For example, reducedness means R0 plus S1 is this famous property, which means like regular in codimension 0 and like almost Macaulay in codimension 1. This is type of property. So this is a singularity property. And so F to the E is injective. And so, but the other thing about reducedness, it means that actually the total field of fractions of R, can be denoted by this, total ring of fractions. It's a product of fields, right? So for this to be true, you see that the R has no embedded primes, right? And when you localize at the minimal primes, what you get are fields, right? So this is a product of fields, right? What this is that you go through all the minimal primes here. So let me denote the minimal prime by P, perhaps. Sorry, R. So you get this. Let's say there are K of them. And so these are fields. So it's a product of fields. So the fact that there are no minimal primes tells you that, like when you do this localization, it breaks down like this. And the dimension 0 hypothesis is that these are fields. So let's call them just like this. So product of fields. Product of fields. So you can also say that a ring is reduced if it is a subring of a product of fields. Are we happy with that? Remember that the total ring of fractions is obtained by dividing all non-zero divisors. Right? It's the largest localization you can do in a ring. And so when this is the case, then what you can do is that you can define the algebraic closure of KR. Right? What you do, you can do that component by component. So this is a product of algebraically closed fields. The algebraic closure, well, I'm saying V, but it's more like the A algebraic closure, right? A ring doesn't have a canonically well-defined algebraic closure. All of them are isomorphic as fields, but it's not the canonical isomorphism. Right, and so inside here, so this implies that we can define the p roots of this ring, right? Like we can, or let's say like the q roots. Okay, let me look. Then what this lets you do is that you can define the cubed roots of R, and these are going to be, what you do is that you extract the cubed roots of R, and you're going to do that component by component here. So this is an element that lives here, right? R is going to be a tuple, and you can take the cubed root component by component in here, and yeah. So this is a subring. So this list is a subring of this huge ring, and it contains R, right? And this is the fact that this is positive characteristic, right? Because how does this work? The cubed root of R to the Q is R, right? And so this is because the cubed root of R to the Q is R. And because we're in positive characteristic, the extraction of cubed roots is a well-defined thing. It's not like in characteristic 0 where you have like possible roots or something. Positive characteristic is a collapse. And that's the convenience there for you. Okay? So and also, right, like when R is an integral domain, there is only one product here, right? That's the difference between reduced and integral domain. There is only one component. And so you can, this is just a field. So you can just do that inside one single field instead of multiple ones. So is this definition clear how this works? You know, like it's just like to define this, you have to do it somewhere. So there is a canonical, there is a choice of the right closures and things like that. And I just don't like that. I just don't like when you have to make choices. It's never wise, like to write canonicity in mind. And so the point is like you have many different notations, right? Like you can say, so if R is reduced, then there are many choices, right? So you can think of Frobenius in many different ways. You can say that you have RQ inside R. You have, well, this one. And then you have Frobenius itself. And the point is that these are all isomorphic as our algebras, if you will. Right? These rings are all isomorphic. And these maps are isomorphic to one another. Okay? So I rarely use any of the other ones. But sometimes it's very convenient. Just sometimes. But to make sense of them, you have to have a reduced ring. Any questions so far? So I'm going slowly because I know this could be the first time you see this. This could be slightly confusing. Okay, let's come back to this. But these other notations have an advantage, right? Which is like the notation for the source and target of Frobenius is different. And sometimes we really like that. So we need one more piece of notation that is going to come up all the time, which is the notion of Frobenius powers. So Frobenius powers so you have your Frobenius, right? And suppose that you have an ideal here. And so you can extend it, right? If you have an ideal, you can extend it across any homomorphism of rings, right? So you can extend it. What is the notation for extension, right? Is, well, you can extend it to here, right? Across Frobenius. So technically speaking, what I'm doing is this. I take the ideal generated by the two powers of A. And that's an ideal of R, right? So this is the ideal, let's say, generated by all the cube powers of elements of A, right? It's just the extension across Frobenius. So the notation we're going to use for this ideal is this. We use A to the square brackets. So if A, so this is easy to compute, right? Like, so if A is generated by, let's say, n elements, then A to the cube is generated by the p powers of the same set of generators. So also don't make the mistake to think that this ideal is literally the set of p powers, of q powers, sorry. It's not, it's generated by those, but this is, if you just write this as a set, it's not an ideal. Okay, so are we good? Is everything clear so far? Okay. Let me know if I'm going too slow or too fast. It's hard for me to cover. So Frobenius is very functorial. So if you have a ring homomorphism or FP algebra map, right? And so you have Frobenius over here, which I guess I'm supposed to write like this. But I never do that. So let's say Frobenius is this magical object in which you can put a ring here, and then you get a ring homomorphism. And so you can see its functoriality here. So it's a trivial statement that it is functorial, but it's deep. So this commutes. Right, because if you have R, you can raise it to the pth, but to the qth power. If you send it here, right, you get phi to the RQ. But if you do it this way, right, you have, and then if you send it back here, you have, but these two things are equal, right? So it is commutative, and sometimes it is Cartesian, right? Sometimes it's a fiber product. So prove that, so it's Cartesian in many cases, but there is a case that is going to be very important for us. It's Cartesian if theta is a localization. Cartesian means fiber product, right? In other words, really no color is good, not even purple. What about red? But let me try to use colors. If it doesn't work, well, it's the same effect as white, so it doesn't change anything. So where are we? Right over there. So just a reminder of what Cartesian means, right? Cartesian means that this is a fiber product or co-product or something like this, right? It means that if you have any other ring homomorphism here, you know, like how do we call it, T, you have a map from here to here and a map from here to here, there exists a unique map. So, and so this being Cartesian, you can put it in these terms. It means that Frobenius commutes with localizations. The localization of Frobenius is the Frobenius of the localization. Right? So this is a beautiful property, right? Because it says Frobenius commutes, it's compatible with the most basic operation in algebraic geometry or commutative algebra, right? Localization is a geometric object, right? If that wasn't true, this wouldn't be a curve. It would stop right here. It would just go home. But it commutes with localization. It's not true that all maps are Cartesian, right? So for example, if theta is a quotient, so it's Cartesian. Well, this thing here is Cartesian. It's Cartesian if and only if the Frobenius power coincides with A, which is essentially never the case, unless the ring is perfect, or it would force the quotient to be flat, for example, and things like that. So, okay, that's going to be important for us. So we need one more piece of notation. I wish things were not this complicated sometimes. So one more piece of notation, which is the Frobenius push forward. Let's just get this out of the way. So what is magical about Frobenius is its push forward. So Frobenius is the following. So the point is that so whenever you have a ring homomorphism and you have modules, over the source, you can restrict scalars and get the modules over the target of the map, right? That's the push forward in algebraic geometry. But Frobenius is super annoying in that regard because the source and the target are the same ring, right? So because of that, we need to be particularly careful with our notation. It's just notation. Conceptually, there is really nothing going on. So the point is that if you have an R module, you push it forward. It's literally the same abelian group. What changes is just the R linear structure, the action by R on it, right? So, but we need to be careful with that. So what we're going to do is that we're going to take the elements of M, and we're just going to put the symbol in front of them. It's just a symbol. It's the same M with a hat, with a sweater. Okay. And it has to be the exact, the same abelian group, right? So what that means is that if you have two of them and you add them together, what you get is the sum, so you can see that if I just say this, right, I define this set and I define the sum, you have the right to say that's completely stupid. It's the exact same abelian group, just with decoration. But the decoration is useful when you have to introduce the R linear action. The way R acts on such an element is by a twist by Frobenius. You have to raise to the qth power. Okay? And therefore, the R structure is completely different. It's a restriction of the scalars by Frobenius. Right? In practice, you can think of this symbol, notationally speaking, as a barrier, right? It's very easy to go in. You just raise by Frobenius powers, but it's very hard to go out. You have to be raised to the qth power to go out across this symbol. Okay? So I guess get used to that notation because it's gonna come up a lot. And so, but the other thing is that's what happens if M is a module. But we have a similar story if M is a ring, right? You can think of M also as an R algebra, right? Meaning that there is a ring homomorphism like this. For example, S could be R, right? R is an R algebra. So the point we want to make is that you can think of this is a ring too, right? Like you can say that so when you do the push forward across the Frobenius of R of an algebra, it is a ring too. It's an R algebra. It's literally the exact same ring as S, but the R action is different. It has a Frobenius twist. Okay, so that's R algebra. So I'm saying this, but the important case is S equals R. That's the case I care most about, right? And so the point is when I write this down, I'm doing two things. I'm looking at the ring R, right? This is just a ring R itself, but the R action is different. The R linear action, the R algebra structure is different. It's given by Frobenius. So, and so the point is that the point is like when you do the scheme theory notation, this makes much sense. But so the point is like Frobenius can also be expressed, right? Let me say is equal to this R algebra. Right, and so what is the R algebra structure? What is the R algebra mark here? Is R goes to, well, it has to go to R1, right? But then it's just this, it's literally just Frobenius. And if you go and look at Hartman, this should be called FE, like hashtag type thing. Is this confusing enough? Or is it clear? Right? It takes a little bit to get used to it. But this is another useful way to write down the target of the Frobenius map as a different object, right? Because what we do is we put different decoration, right? In the case R was reduced, we use this notation literally, right? But what is that? It's just R1/Q, and it's just different notation, right? Like you can use this sweater, or you can use that sweater, but it's up to a change of notation. It's the exact same thing, right? So, okay, so it's in this business is always very annoying. You have to go and give a talk. You always have to explain this, and it's so annoying all the time. Of course, at least I talk to non-experts. So. Okay, so that's great. So now that we have that notation, so I can say things like this. So in singularity theory, given Kunz, like that's what we're going to see in a second. We care about the R modules. So we have all this family of R modules that we would like to understand. Okay, and so for example, you can translate now the thing I was telling you about R being reduced, and now you can say that R is reduced if and only if these R modules have a particular property, which is that they are faithful. Is faithful for all E. Well, for some equivalently all. When I write this, I mean like it is true for some, but if it is true for some, it's true for all, automatically. Okay, so what does faithful means? Faithful means that, well, the annihilator of the module is 0. Okay, or in multimetric terms, the module is supported everywhere on the spectrum. Okay, so you can see that the module theoretic properties of these guys start to tell you about the singularities of your ring. Okay, it's a simple observation, but conceptually it's very good. It's very satisfying for singularity theory. Thus, it means that Frobenius is wise; it can see things, but otherwise it'd be hard to see, like whether or not the ring is reduced. So, any questions so far? So with this, I can make an observation about Frobenius and completions. So Frobenius and completions. So we saw that Frobenius is friends with localizations, and so it's also going to be friends with completions in a very specific way. Okay, so suppose that you have a local ring. Local theory, right? Local theory. So we saw the other day that we can complete that ring. And we didn't change the residue field. The maximal ideal is just the extension of the maximal ideal, and this is spatially flat. So everything is awesome, right? So we can take a module and we can complete it too. And so this is a functor. This is the functor of completion. Maybe it's not a map, but there is a map too. So let's say that you get a module, and this m hat is given by the inverse limit, which is n. It's maximal ideal to the m power n. And so you can see that this is an r hat module. R hat module. Okay, so that's the completion of the module. So you have all the theory or the category of modules here, and you can just complete it and get modules here. And so you may say, but I know another functor around there that does that, which is pull back. Instead of completing them, you could have pulled them back, right, to our hat, or do a base change. So these functors are related by a natural transformation. So let me go all the way here. So this is a remark, right? Like, so then you have, well, you could have done this, right? You could have done a base change. So this is base change. What am I doing? This is M. And so there is a canonical map here to M hat. And so in other words, there is a natural transformation from base change to completion of modules. So this is a functor. So if you have, like, it's going to be compatible with homomorphisms of modules, the usual way. So, but you know that this may not be an isomorphism, but there is a particular case in which it is. Right, so this is an isomorphism if n is finally generated. Okay, you guys remember that? Maybe else you can look at that J. McDonald chapter on completions. I think there is an example there. But in principle, this is a much larger module, let's say. Okay, and so this is what is happening here. So the theorem is an exercise. So if you take this module, right? It's an R module. Here I'm assuming that R is local, right? So to do a completion. So you can complete it, right? You can go ahead and complete the spin. So there is a canonical map that goes, the canonical map goes which way? Okay, well, you can ask what is the relationship between this and the Frobenius of R hat. The canonical way is it's like this. I think it's like this. There's a canonical map. Yeah. So I'll let you define it, but there is an isomorphism of R modules, R hat modules. Okay. In other words, the Frobenius of the completion is the completion of the Frobenius. Okay. If R is not even actually, otherwise is a little bit of a mess. So so this let us see a particular case, and actually we're going to come back to it later. But what you can see that, so for example, you can go ahead and write down the following diagram. You have your completion. You have your Frobenius, and write down like this. This is your Frobenius. Let's use this notation from now on. Why not? And so you can go ahead and write the tensor product. So this is going to be Cartesian or hat. You can go ahead and do the space change of R. And over here, you have the completion Frobenius. So this is Frobenius hashtag for this time of the completion. For R, oh, sorry, it's F to the E hashtag. Right? So, yeah, there exists a unique map going this way, right? And so the question is, when is this an isomorphism? So if it's a final generator R module, then let's give this guy a name. Actually, it's the relative Frobenius of the completion. When we define that in a second. So then let me call it like this because that's what it is. It's the relative Frobenius of the completion. It's an isomorphism. So then it's an isomorphism. So this is something we're going to call a finite. So when the ring is infinite, you can say that the base change of Frobenius under completion is the completion of the is the Frobenius of the completion. But you need finite generation for that. So that's actually one of the reasons why finite rings we're going to see are so prominent in the theory. They give you so much stability, in your life and everything. Any questions so far with that? So, that let me come back to the thing we were saying about the Frobenius being functorial, and that's going to let us define the so-called relative Frobenius that we're going to be studying from time to time. So, okay. So it's the following. So suppose that you have another ring homomorphism. Let's call it theta. So you have your Frobenius. You're calling this like a T hashtag R. Then you can do a base change. You can base change this whole thing, and you get this ring. Right? But you can write down the Frobenius of S here. And here, you can have, if you will, the Frobenius push forward of theta. Right? So this is what you think it is, right? If you have Fe lower star little r, you send it to Fe lower star theta of r. But let me just run out of that. So this is the math that takes, it's literally just that. Right? And so then you get a homomorphism here, right? There is a unique map here. What is that map? How does it work? So you have this map, and what it does is the following. So if you have S tensor Fe lower star little s, this goes well. Sorry, not here. I did something wrong. It's R here, right? Yeah. So it's going to be something here, right? And so what you do is that S is goes to Frobenius. So S is going to show up to the cube, and R to the, it's going to be the application of that, right? And this guy here is also known as the Frobenius of the extension. It's a relative Frobenius. So we're gonna, if you want, we can call it like this. Or maybe with a hashtag if you want. I think at some point we're just gonna start dropping the hashtag. It's too annoying to write down all the time. So this guy here is so-called relative Frobenius. And so what we notice is that for localizations, it is an isomorphism. And for completions, it's an isomorphism when the rings are finite. Okay? So actually, I've been writing a paper for a very long time, and we have a preliminary section. It's very cool. How we post it on the archive soon. When we characterize or discuss exactly when this happens. For what ring homomorphism is a relative Frobenius, an isomorphism. And it's very cool, actually. I'm going to let you prove as an exercise that this is a very important property this has, is that this is a homomorphism. It is, if you know a bit of spin theory, you can prove it is a universal homomorphism too. So, yeah, I think that's all I want to say about Frobenius. Any questions so far? Because I think that the rest of observations I would make is when, you know, these guys are finally related, but that's going to be a topic for later. It's for next week. So yeah, so Frobenius is this thing that we gotta get familiar with it because of the following. So this is Kunz's theorem. So theorem. It's a rather old theorem. It's from 1969, but it's the genesis of the theory of F-singularities. Okay. So it says that R, a theorem ring, is regular if and only if the modules I was telling you about are flat. For some equivalently OE. I'm going to let you as an exercise that if you know for some, it's true for all. So, remark. So, if you have an R module, is flat if and only if tensoring with M is flat. So in other words, like the other way to think about this is to say that the Frobenius matrix is flat. Base change by Frobenius is a flat operation. You preserve exactness. Okay. So, and let's say a few words of why this matters. This has to be appreciated. It's not just about okay, whatever. It has to be appreciated, right? Because here you have this property that we want to understand, right? It's so fundamental. Is what makes things work. And you want to know what it is equivalent to. And so on the other hand, you have this module, or shell, this map, whose flatness characterize that. And so that's in particular great because flatness is the most basic property in commutative algebra. It's exact. It's exact, yeah. Sorry. Exact. Right? Flatness is the most basic property in commutative algebra. Think about how it grew up. Right? So think about like very naively, right? Like you have, think about your courses, right? Like how you went through linear algebra and you knew the theory of modules over a field. You understand that, everything is great. So you move through rings. And what do you think is the most important property a module could have, based on linear algebra? That it is free, right? You may think, oh, that's free is the property, to understand. But not really. Commutative algebra real quick tells you, For example, when you look at projective resolutions, you will learn that it's not free what matters. It's projectivity. And you say, it's projectivity most definitely what matters. But then real quick, you learn that, but I didn't have an example, but you're supposed, this was supposed to be the moral of your commutative algebra courses. You learn that projectivity is not what matters, it's flatness in general. Flatness and projectivity only agree in finite context. If you want to go to the general context, flatness is the key property. It's mysterious, right? It's mysterious. It's the exactness of a very important functor, which is tensoring, right? But it's the key. After all, flatness is this freeness notion expressed homologically, right? What you're saying is a certain x, not x, sorry, Tor functors vanish, right? Well, it's a homological property, I guess. Right, I think probably we'll have that experience when we encountered flatness for the first time. It was so mysterious, and so what is even a flat module, right? That is not free and projected. But it's the key property. It's the most basic property in commutative algebra, and that should be the moral of the commutative algebra class. That flatness is the property, of excellence for a module. Okay. And all properties should be understood as deviations of that, in a sense. So, and therefore you have this theorem making this, equating these two worlds. So we're going to try to understand the absence of regularity, but now we can do this through the absence of flatness. And all of a sudden, we gain a whole bunch of new techniques to do that, right? Because we have a huge arsenal of basic algebra to understand this notion, right? Books and books have been written about flatness and homological properties and whatnot, right? So, and think about it, right? This phenomena here of regularity or singularity is just insane. Just think about how many ways you can be singular. Now it all reflects into Frobenius somehow. So it's definitely a beautiful, beautiful theorem. So I can tell you that when I was a student and I saw that for the first time, I got completely hooked by it. I couldn't believe my eyes that this could be true. And I just love it. I got to it by accident, actually. When I was doing a PhD, it wasn't supposed to work on that, but it just happens to be all about it after all. So, Okay, so they follow the. I don't know if we're going to have time to do the hard part of the proof. So I think then what we could do is to start doing the easy parts. Because I don't want to leave the hard part like sort of like broken. Any questions so far with this theorem? Yeah, actually something again in proof. I don't want to say because I haven't written down the proof. Right? This is true. I haven't seen this written down anywhere. So, but I think perhaps it's gonna show up in a paper of mine, the same paper I'm writing down. Like you can say that R over FP is formally smooth. So it's a weakening of regularity being formally smooth. It equates the forbidden being projective. For example, so you can see that this goes deeper than that. So what I'm saying is like there is this filtration of weakenings of regularity, and they sort of correspond to the weakenings of this notion. It's so cool. So okay, so that's the easy part. So what do you think is the easy part? The easy part actually is easy, right? Easy. It's relative to the convert, let's say. So the easy part is that if it is regular, the natural observation is that this is flat. Let's do an example. What is the most regular ring ever? What is the regular ring for excellence? An easy one, polynomial ring, right? So take R equals a polynomial ring. For example, this was the first ring ever for which finite law of dimension was shown. This is the Hilbert system theorem, right? Which we now think of the notion of regularity, finite law of dimension, right? So, well, I told you, but I think that I said that the other day, that this ring can be thought of as a direct sum of this, where you take this to be simply non-negative integers, right? And the ring operation is just like the monomials and so on. But what is the thing? The thing is that now you use the Euclidean theorem, right? If I give you an integer I, it is uniquely expressed as qj plus some residue, let me call the residue k, where k goes from 0 to q minus 1. There's a unique decomposition, like that, right? Elementary school. So now you can express the Euclidean theorem by showing that this is free. It's beautiful. It's absolutely beautiful. So what I'm going to do is that instead of, I'm going to write down two different sums. So first, I'm going to go through all possible residues. So I'm going to say, okay, I'm going to take K1, Kn, and then I through K minus 1, and then all possible portions. Then I'm going to go through J1, Jn, right? I'm going to write down K, and I'm going to express, instead of i's, I'm going to express using K and J. So it's going to be Q. I don't have a number on my thing. Is it okay if I use multi-index notation? If I just write x underline to express x1 through xn, and then it's gonna be, where is it? How's the word? Is Q J underline plus K underline, where this is J underline, this is K underline. So, okay, so you do that, right? And so, and then we go all the way to the other side. Okay, so that's fine, right? That was just the composition of my indexes. And so what you get, let's say the direct sum over the case, and then okay, let me do a change here. So it doesn't matter, it's the same thing. So this implies that the Frobenius of R, so it's gonna be this sum over the case, and a big sum over the j's. Oh, the j's no boundary, right? I didn't say that. Yeah, so the j's are simply natural numbers, right? And all possible portions, all possible residues. And here, I'm going to have Frobenius of K, and then this x1, qj1 plus k1, xn, qjn plus kn. And then what it is. So is this sum. Let me just write down over the case, okay? It's the same thing. Then over the j's. And what happens? Now I can take the q out, right? And so what happens here is that we are going to have so okay, K x1 okay, I take the x1 j1 xn jn, and so inside here I'm going to have this module which is k times x1 k1 xn kn. Are you with me? And so what is slightly annoying is that now I'm going to need a basis. So now look up. So look at this. This is a field, right? So this is just a k module over k. So it has a basis. Okay, so let me say that. Let me just say that I can hook up a basis here, right? Like Frobenius is free for fields, right? That's another thing one has to check, that for fields, Frobenius is free because fields are regular, so it checks out, right? That's another proof that fields are regular. Therefore, Frobenius is a field. So then you can hook up a basis. Let's hook up a basis. So let's choose some lambdas and some big lambda, whatever, right? And so I can do one more step. It's so annoying. So I could have assumed that k is perfect to avoid the steps here. And now what I'm going to do is that I can take this sum here, and now I can put k in front. Let me say x j bar. And here I'm going to have this little lambda. Well, a big direct sum on lambda too. Let me do this direct sum over here. Lambda in lambda, k is j's. Okay. Let me use multi-index notation again. K, right? And so with that in place, all I need to say is that when you look at what you got here, right, it's just a copy of R. Right? And so this is to say that this guy is free over R, and the basis is just given by the Frobenius push forward of lambdas times the x to the all possible residues. That's it. So upshot. Remember this because it's going to come up later. Upshot. The Frobenius of the polynomial ring is free over R with basis. Let's write it down. And what you do, so what you take lambda and lambda, so you have to choose a basis for the ground field. Oops. Right? And then you let the case run from k n to q minus 1. Okay, so for example, let's say the residue field is perfect. It just means that this is an isomorphism. That's what it means to be perfect, right? That the Frobenius is an isomorphism for the field. In that case, lambda is it's empty. It's empty, or no, it's generated by 1. Okay, it's 1. And so in that case, you see that it is free, and the rank is q to the n. Okay. So you look at that and just say, okay, how general is that? So it is clear that that's a general picture, right? It's similar to the Hilbert-Syzygy theorem, right? Like in the Hilbert-Syzygy theorem, you had like, okay, how do my polynomial ring? I can find a free resolution of length at most n. For what rings is that true? And then you realize, oh, it's only for regular ones. Great. So it's similar here. You see that the Frobenius is free for the polynomial ring, particular flat, and you can say, okay, so when is this true? It's kind of just for regular ones. Okay, so let's go to the proof of Kunz. So this is the thing. There are a few reductions we need to do. So few reductions. So you look at this module, right? And suppose that you want to prove that it is flat. What can you do? You can localize. So it's flat. A module is flat if and only if its localization is flat. Right? Because flatness, is expressed by the vanishing of certain tors, and you can put that those are 0 by localizing is exact. And so, right? So flatness is a local property. But what do we see? Frobenius commutes with localizations. So this is none other than RP. It's an RP model. This is flat as RP model, right? And so you have to prove that this is flat as an RP module. Okay. In other words, we may assume that the ring is local, because regularity, by definition, can also be checked locally. Right? By definition, a ring is local if and only RP is regular. Sorry, a ring is regular if and only RP is local for all RPs. So if you look at this, so we may assume that R is local. We have to compare two properties, and these two properties can both be checked equally. So what is the other step? What do you think? Once you have local, what do you think? I was talking about completions. We may assume that R is complete. We can complete. So suppose now that we are in the local case. Very local. And I want to prove that this is flat as an R module. It turns out that if this is flat, its completion is flat. So it's flat as an R hat module. So so I don't think it's quite true that in general, is it just like that completion always preserve flatness? In this particular case, yes. But it also has to do with it being faithfully flat. This module. It's not just flat, it's just faithfully flat, and so its completion is flat. But this is the step. So this is flat, and then you say, oh, but this was just M hat. Right? So if the Frobenius is flat for the ring, it's flat for its completion. Let's look at the converse. Let's look at the converse. So for that, I'm going to come back. So the converse would follow right away if we were dealing with finally generated modules, actually. Because if you have something and you do a faithfully flat base change, and you have something flat, it's flat to start with. But we don't have a final generated thing, so the base change may not be the completion. So that's why you have to be careful with. But the converse, for the converse, you look at this. So you have Frobenius. And so this is the thing, like this is faithfully flat. No, sorry, this one is faithfully flat, right? And I would say that the Frobenius commute with completion, so this is a completion. So what? This map here is just take this and you complete. So this is faithfully flat as well. And so by hypothesis, you would say, okay, what if this is faithfully flat? Then this composition here would be faithfully flat. And it turns out, I guess I'm going to put this as an exercise, if you have a map of rings, or a map of algebras that are faithfully flat over a common base, that map has to be faithfully flat. It's a general property of faithful flatness. So it would imply that this is faithfully flat. So if you know that the completion has a faithfully flat Frobenius, then you conclude that the ring you started with has a faithfully flat Frobenius. So this property here it shows up when it's a famous property for the étale topology to work. Like it's sometimes when you have étale, the span has to be étale. It's the same for faithfully flat. It's part of the reason why these faithfully flat ring maps give you a topology. This FPPM topology or some combination of those letters. But it's well established that this is how it works. So in conclusion, we may assume that R is complete. Okay. So in other words, both properties of regularity, and the regularity can be checked up to completion. We saw that, right? Like a local ring is regular if and only if its completion is right. So we may assume complete. So flatness of Frobenius respect the same sort of property because they are equal, right? Secretly, that's what we're trying to prove. So, and so, so then you see why if R is regular, the Frobenius is flat because of who? The coordinate structure theorem. So if R is a complete, let's say, if R is complete regular, then it is isomorphic to the power series ring. And similarly to the polynomial ring, one can prove that this has a flat Frobenius. However, I don't think the same proof is going to give you a free basis. You only know that Frobenius is flat. It would be so that the issue has to do with whether or not the basis you could come here from the Frobenius of the field is finite. But you can do the following. So you start with this polynomial ring. Let me do this step real quick. So what you can do is that what the argument we just wrote down proves to you. So here there's a relative Frobenius in between. That this is free. Free of rank Q to the n. Like the argument we just wrote down. That's fine. Like this is the Euclidean algorithm part of the thing. Like you know that the power series, what is the difference between the power series ring and the ring? It's not the direct sum, it's the product. So, but you can do the exact same argument here. You have to be careful when you get something free. But then, what you do is that you do a base change. And this is what you have to be careful because it is a product, it's not a direct sum. So base change doesn't commute. Right? Base change commute with direct sums, but not with products. You have to be careful. Okay. So you do a base change. But base change by a field is flat. Right? So this is flat. And the next step is like, well, it doesn't commute. So then you have this ring. This ring is the full Frobenius, right? This whole thing is the Frobenius. So the last step is this. So here, what this is actually, this all the way here is the relative Frobenius, and this is the canonical map. But the difference here is that this is a completion. So maybe I'm going to explain that a bit more in the next step. But it's flat. Basically flat. So the whole thing is flat. Another proof can be obtained as follows. Here's another proof, right? Like you know that the Frobenius of the polynomial ring is flat, right? We just proved that. It's not just flat, it's free. But then you do a completion for the polynomial ring to obtain a power series ring, right? And therefore, what you get is flat. It may not be free, but it's flat. So you see, like it's free. This is free, but there is this big chunk that destroy the flatness. Okay, but that's how the proof. How does the proof go? There is this completion part there, right? Like, and it has to do with the fact that this is not finite derivative, and the power series is not a final process; it's an infinite one. And so you have to do a little completion there. Okay, let me think about it. This is a good thing to think about it. I think we're over time, right? So yeah, so this proved the easy part of the Frobenius statement. And next time we're gonna see the substance of the Frobenius theorem, which is like, if Frobenius is flat, how on earth is that ring regular? Okay, and so that's what we do next time.